Okay, so we finished the neuromuscular junction. You know the importance of the axon terminal. You understand that in the axon terminal, you have the end bulbs. In the end bulbs, you have the excitatory neurotransmitter called acetylcholine. It gets released because calcium influx into the end bulb tells the neurotransmitter to open up through exocytosis, releasing the acetylcholine. It's going to move into the synaptic cleft, bind to the acetylcholine receptor or the sodium channel. Sodium rushes in, creates depolarization, action potential goes down the transverse tubule. Transverse tubule binds against or butts up against the sarcoplasmic reticulum. It's going to release calcium. It's going to create this troponin tropomyosin shift. It's going to pull out troponins, so tropomyosin shifts, exposing the binding site, and muscles can contract. Okay, that's pretty much what happens. In order to end it, right, you have to use the acetylcholine esterase. Okay. So myosin pulls on actin, causing the thin filament to move inward. Thanks to those structural proteins, right? Thanks to the structural proteins, there is a transmission of force throughout the entire muscle, resulting in the whole muscle contraction. So what we see here in the contraction cycle is that right here, we see that the myosin head is reaching upward to the binding site on actin. Here we can see in green, these target sites are all exposed because troponin and tropomyosin are moved out of the way. But pay attention here. Look right here. ADP is adenosine diphosphate, and hanging out here right next to it is CP, or creatine phosphate. When you have too much energy or too much ATP, your body can store that additional phosphate as creatine phosphate, or CP. In this case, it's just P. So you have ADP, adenosine diphosphate, and the phosphate hanging out. Now notice that here, the myosin head now flicks. It moved the actin. It created a contraction. They call it the power stroke. Now, in order to release it, what is needed, look, the ADP and that additional phosphate join, forming ATP. If you have adenosine diphosphate and you add a third phosphate there, you have adenosine triphosphate. That's what is needed to detach the myosin head from the actin, getting ready for another power stroke, right? It's the detachment that it requires ATP. Now, in terms of muscle metabolism, how do muscles derive ATP that's needed? CP, which is creatine phosphate, which I mentioned here, that's creatine phosphate. That's for immediate energy. Doesn't last very long. It's like a power lifter, quick impulse. It's not for endurance. We have anaerobic glycolysis, right? Glycolysis, lysis means to break down, breaking down sugar, glycolysis, and we'll talk about cellular respiration as well. So here we have this creatine phosphate. Now, creatine kinase, anything that ends in ACE, is an enzyme. So creatine kinase catalyzes the transfer of a phosphate group from creatine phosphate to ADP. Okay, so here we have creatine phosphate. Here's creatine. You have creatine phosphate that can hook up with ADP. So when you have ADP, adenosine diphosphate, and it's joining creatine phosphate, an additional phosphate, you get ATP. Okay, so when you have creatine and you have too much ATP, this phosphate can join creatine. Now you have one less phosphate here, which is why you have ADP, adenosine diphosphate, and the creatine and that third phosphate now become creatine phosphate. Creatine phosphate can then be acted on by creatine kinase here or here. So it could be used to make or break these bonds. Okay? When you have too much energy, ATP, your body can donate one of these phosphates to creatine, creating creatine phosphate, and then ADP is just like it's potential energy. It's ready to be used once it hooks up with another phosphate from creatine phosphate. I have ATP. Now the energy is used for muscle contraction. So at rest, right, a muscle produces more ATP than it needs, so it's going to transfer some of that energy or a phosphate to creatine. So you have ATP plus creatine, you're going to get ADP plus creatine phosphate. Here you're going to have ADP plus creatine phosphate. You're adding a phosphate to ADP. Now you get ATP and creatine hanging out. Okay, here's the creatine phosphokinase, that enzyme. Now, creatine phosphokinase is an enzyme that's hanging out in muscles. It's in skeletal muscle, but it's also in cardiac muscle. So if this is a membrane, let's say a heart muscle, and this heart muscle has some CPK in it, and if this muscle ruptures and you release an excessive amount of CPK, and someone is having chest pain, they're going to look at CPK levels. And if CPK levels are high, they're going to be saying, we think the person may be having a heart attack because muscle cardiomyocyte membranes must be rupturing, releasing more creatine phosphokinase into the bloodstream than normal. Okay, so that's why they look at enzymes to determine if someone's having a heart attack. They can tell if they're having one, if they've had one and they're recovering, depending on the levels. So in terms of cellular respiration, you have to remember that glucose can be broken down. We call that glycolysis. When you break down glucose, it's broken down into pyruvic acid. So you're taking a 6-carbon sugar, glucose, breaking it down into 2 3-carbon sugars called pyruvic acid. Now, as long as you have oxygen available and you're breathing and you're not out of breath, huffing and puffing, pyruvic acid can enter the mitochondria. If you're out of breath, you don't have enough oxygen, or you're in an oxygen debt, pyruvic acid is not moving into the mitochondria. Instead, glucose can turn into lactic acid. Okay? So if oxygen is available, lactic acid can become pyruvic acid. Just happens in the liver. So pyruvic acid enters the mitochondria, enters the Krebs cycle. You make some ATP there. The Krebs cycle gives off some coenzymes that enters the electron transport chain. The electron transport chain produces a whole lot of ATP, a whole lot of energy. There's some ATP that's made from glycolysis, some ATP that's made by the Krebs cycle, but most of the ATP is made by the electron transport chain. Glycolysis takes place in the cytosol. Remember, the cytosol is within the cell, right? You have the cytoplasm and the cytosol. It's the liquid stuff between the cell membrane and the nucleus. That's the cytosol. But the Krebs cycle in the electron transport chain, that's happening in the mitochondria. Okay, here's where CoQ10 is needed. Coenzyme Q10 is really needed for the electron transport chain. People that take these statin drugs really deplete and damage their mitochondria. They don't have enough energy, and then their muscles hurt and their joints hurt. The Krebs cycle requires a lot of your B vitamins, B1, 2, and 3, B1, 2, and 3 for energy, the Krebs cycle. Okay, so I just mentioned statin drugs because a lot of people are on cholesterol-lowering medication. I want you to understand that there's a consequence for everything, right? So not too long ago, I had a patient who I saw recently, but before I saw her maybe like a few weeks before that, a month or so before. This time she came in with a cane. and she was complaining of severe, severe hip pain. So I said, her name was Pat. I said, Pat, everything okay? She goes, I got such joint pain in this hip. I don't know how I didn't fall. I had no trauma. So when she came in the room and I examined her, the hip was perfect. There was nothing structurally wrong with it, but it was sensitive. So when there's nothing structurally wrong, but there's still pain, it's biochemical, something chemically induced. So I said, any change in medications, drugs, vitamins, nutraceuticals? She goes, I started a new medication a few weeks ago, about 2 weeks ago. I said, a statin? She goes, well, I don't know what a statin is, but he did put me on a cholesterol medication. I said, what's the name of it? And she said, simvastatin, right? There's the word statin, simvastatin. So I want you to see what ends up happening. So acetyl-CoA becomes HMG-CoA. HMG-CoA goes to mevalonate, and then you see this whole biochemical process in order to make cholesterol at the bottom. But in the same biochemical pathway, not only are you making cholesterol, you're making CoQ10. This very important biochemical pathway is not just need to make cholesterol, but CoQ10, and CoQ10 is needed by the electron transport chain to make energy. So a lot of people end up depleting CoQ10, and the mitochondria can't make enough ATP. And where do you find the most mitochondria? Muscles, skeletal muscle, cardiac muscle. So her hip pain was coming from the large muscles around the hip joint. When I told her to go back to her primary and explain what I had explained to her about a CoQ10 deficiency and to consider changing the medication, I had given her a higher dosage of CoQ10 called ubiquinol to take, and she said in less than 2 days her pain was completely gone. So we knew that it was induced by the statin drug. Once she took the CoQ10, her symptoms went away. The doctor changed her medication. The problem never came back. I had another patient who developed cardiomyopathy that created heart disease from the statin. And when you look at the timeline of the history, it's not heart disease happened first, it was cholesterol. They took a statin. Shortly after the statin, they ended up developing heart issues. Then they were on a heart medication. And then shortly after that, it was downhill, not good. So those of you that are getting into healthcare and getting into nursing, I teach you this so that you have some of these clinical gems to keep in mind, but it may actually help you now with family that may be dealing with it. When you have muscle pain, they call it myalgia. You've heard of fibromyalgia. When it's nerve pain, it's called neuralgia. When it's joint pain, it's called arthralgia. Anything that ends in algia means pain. So if you look at the black box warning, you'll see arthralgia, myalgia, neuralgia as an adverse reaction to statins, along with dementia-like symptoms, where they get cognitive issues because the brain is largely cholesterol. So there's a lot of downward effects to it. And then remember, the cell membrane has a large percentage of cholesterol in every cell membrane wall. So understand your anatomy and physiology. Just FYI, the statins are blocking an enzyme called HMG-CoA reductase. Remember acetyl-CoA to HMG-CoA? Then HMG-CoA can go to mevalonate, but if you block this step with a statin drug and you block this enzyme, nothing below this arrow takes place. That's the problem. So when creatine phosphate stores are depleted, glucose is converted to pyruvic acid to generate ATP. Okay, so you have glycogen, which is in muscle. Ogen is inactive. It can be converted to glucose. Glucose is broken down by a process called glycolysis in the cytosol and becomes pyruvic acid. Pyruvic acid, if there is no energy available because there's no oxygen, the body converts pyruvic acid into lactic acid and be converted back to glucose. So this is under anaerobic, meaning there's no oxygen available. You're in an oxygen debt. You get lactic acid accumulation, which gives some people a little bit of fatigue when they're exercising and they have no more energy. So that gets converted to lactic acid, goes into the blood. You're breathing, you're huffing and puffing. After about 3 to 4 minutes or so, your breathing slows down, your oxygen levels go up. And when your oxygen levels go up, you're now in an aerobic condition, where pyruvic acid from glycolysis can enter the Krebs cycle and the electron transport chain. Even from fat, your fatty acids can be used for energy, and your proteins can be used for energy from amino acids. Now, you really don't want to break down your body protein for energy. This is when someone is chronically sick and they're not eating. You start to see the zygomatic bones of the skull. You start to see the effects of sarcopenia, where muscle tissue is being used for energy because the patient isn't eating, right? So you never want your body utilizing its own proteins for fuel, because it's going to digest its own organs, and that's organ failure, right? That's why you always want the patient eating, getting nutrition from the outside world. So when lactic acid is recycled, we call it the Cori cycle. The removal of the recycling of lactic acid by the liver. Remember, I said the liver is being utilized to convert lactic acid back to pyruvic acid. And glucose is released to recharge muscle glycogen reserves. So here in the muscle, we have glucose that can be converted into pyruvate. Pyruvate, as you're exercising, when you become anaerobic and there's no oxygen available, pyruvate becomes lactic acid, and you go, I need a break. My muscles are burning. I have no energy. I got to take a break. Let me catch my breath. So that lactate goes into the blood, goes into the liver. You're huffing and puffing. It's slowing down. You're getting a little bit more oxygen. Lactate goes to pyruvate, back to glucose, and glucose can be used by the muscle for fuel again, because glucose is broken down by the process called glycolysis or glycolysis to become pyruvate. Pyruvate enters the mitochondria and you have fuel. If you're in an oxygen debt, it gets converted to lactic acid or lactate, and this cycle continues. It's called a Cori cycle. In terms of hormones and muscle metabolism, growth hormone, really important for muscular development. Testosterone is very important. Thyroid hormones are involved with muscle contractions, as well as the sympathetic nervous system and epinephrine. Growth hormone is released when you sleep, right? So about 50 minutes after you sleep, growth hormone has its impact to regenerate muscles, tendons, cartilages, everything. But if you consume refined carbohydrates or sugar or ice cream or a cookie right before bedtime, you block the whole thing. It blocks the receptors. There's a lot of exercises that could be done to increase testosterone. Bench pressing really boosts testosterone levels. Squats really increase testosterone levels as well. Thyroid hormones are really supported by iodine and selenium. It's really important for the thyroid to be nourished properly. It does need iodine, and it does need selenium to function properly. When there's fatigue, what are some of the things that can kick in or that can create muscle fatigue? You don't have enough calcium, right? Inadequate release of calcium from that sarcoplasmic reticulum. You can have depletion of energy or creatine phosphate. You can be out of breath. You don't have enough oxygen. Or maybe you're iron deficient. You don't have enough iron. You don't have enough calcium in your diet. You don't have enough B vitamins. You don't have enough CoQ10 for energy production. You can get the buildup of lactic acid and adenosine diphosphate, or an insufficient release of acetylcholine, that neurotransmitter, at the neuromuscular junction. So why do you continue to breathe heavily? We went over this before, right? Why do you continue to breathe heavily for a short period of time after you exercise? It's to kind of get back your oxygen. You want to pay back the oxygen debt from overexertion. And the extra oxygen is going to go to replenishing the creatine phosphate. It's used to convert the lactate back into pyruvate with the Cori cycle, and is going to reload oxygen onto myoglobin. In terms of muscle tension, every muscle is going to have muscle tension, especially your postural muscles. In terms of strength of a muscle contraction, that's really going to depend on how many motor units are activated. So if you're lifting something light that's not too strenuous, maybe 1 or 2 motor units. But when you're lifting something heavy and you have to overexert, many motor units activate. So activating only a few motor units will generally result in a weak muscle contraction. When you activate many, it will be a stronger muscle contraction. Here is a motor unit that we're looking at. Here we can see that this is the spinal cord, and now you have somatic motor neurons going to the end plate of the muscle. In terms of muscle tone, right, even when you're at rest, muscles have a certain degree of tension. That's called tone. When muscles have too much tension, we call it hypertonic. When it has too little tone, we call it hypotonic. I was taking care of a baby a few weeks ago that had hypotonic cervical muscles. The head would just drop. And after 2 or 3 treatments, all of a sudden, the brain, we were doing treatment to activate the brain, the motor cortex of the brain, and the baby's cerebellum, and the head was able to hold up. It was really refined, complicated work to activate the brain, but also activate the eyes. There was a disconnect between the eyes, the brain, the ear, and the postural muscles of the neck. And once we were able to work with the mother and the baby, it was a night and day difference. But before that, the baby was having, the flat skull because the head was always rotated in one direction. So it was a night and day difference. It was a great family, been taking care of them for a while. They own a local CrossFit gym nearby. So it was they were very grateful. Okay, let's take a break here.